Okay, in this lesson we're going to address what is called the heat of formation for an element. And that by heat, I'm using heat as the word enthalpy. I'm using them somewhat interchangeably here. This is the enthalpy of formation, and also something that your textbook at home calls Big Mama's equation, but a way to calculate the enthalpy of a reaction from the enthalpy of formation. Okay, as we start talking about enthalpies of reactions, we're going to do a little review. This is a heating curve or a cooling curve, depending on which way you look at it. If you look at it going this way, it's a heating curve. If you look at it going this way, your substance would be cooling down and it would be a cooling curve. We've seen this last year. At our lowest temperatures, we have solids. In the middle, we have a liquid. At the highest, we have a gas. And that is because at our lowest temperatures, our molecules have low energy and they're all hanging out together. We can heat up our solids, and if we were to calculate the heat added to a solid, we would use our MCAT equation that we just revisited in the previous lesson. Once you get to the melting point, which is the same as the freezing point, depending on which direction you're going, your temperature stops changing, because at this temperature, and this happens to be the heating curve for water, so the melting point and the freezing point are zero. At this temperature, when you start to add energy at this temperature, something magical starts to happen. All the energy then is used to separate the intermolecular forces that are holding your solid molecules close together. And because that energy is used to separate the intermolecular forces, it can no longer increase the kinetic energy of the molecules. When you have a substance in one phase and you heat it up, you are increasing the kinetic energy of those molecules. All temperature is just a measurement of kinetic energy. This is a review from last year, but it was the beginning of last year that we talked about this. It's a measurement of Ke for kinetic energy, energy of movement. So as you heat something, you make those molecules move a little bit faster and a little bit faster, and their temperature goes up. But once you get to this point and something starts melting, that's a magical point, because then you've added enough energy to start making the molecules move farther away. Then the energy that you're adding as you go along here, as you continue to add energy, is no longer making these move faster. It's separating their intermolecular attractions. It's being used for something else. So the temperature doesn't increase until they're all separated. At that point, if you add any more energy, it can then make them move faster. And that's when you would heat up a liquid. Once you got to a certain magical temperature, for each substance it's different, it's called the boiling point, you will then cause the molecules to move farther apart. That's when you're going through a phase change. So again, when you get to these phase change temperatures, you're no longer making the molecules or the atoms move faster. The energy you're adding is separating their intermolecular attractions. That's why the temperature does not increase or decrease during a phase change. It's all reverse when you're cooling down, which we're kind of ignoring right now. When they're all a gas, all in the same phase, then if you add any additional energy, it can increase their kinetic energy, which would increase their temperature. In previous lessons, we talked about heating up things in a solid phase. Now we're going to talk about, briefly, before we talk about other things, the molar heat or the enthalpy of phase changes. These are one type of enthalpy. We can calculate them and look them up in a table and then use them. If you know the molar heat of fusion for 1 mole and you have 3 moles, you can calculate the molar heat of the 3 moles that you have. You just multiply 3 moles by your molar heat of fusion. We've done that in the past. I'm not going to do it again right now. My point is that I'm going to make this smaller. That one type of enthalpy that we measured last year were the enthalpy of phase changes. You had the enthalpy of fusion, which is melting, the enthalpy of vaporization. These are different types of enthalpies for showing you the enthalpy of certain reactions. In this case, for fusion, it would be water going from a solid to water going to a liquid. For vaporization, it would be water going from a liquid to water going to a gas. The energy in the bonds that are holding the water together are different in different phases. We also, let's take another slide because this doesn't relate to a heating curve. We can also measure the enthalpy of combustion. This is another type of reaction. So if we were going to combust, let's say, propane, we would combine it with oxygen. It would make CO2 and O2. Let's try to balance this really quickly. I think that's balanced. So somebody in the lab could measure the enthalpy of combusting 1 mole of propane and put that in a table, and then we would know what that was. And if we had 2 moles of propane or 3 moles of propane, we could just go look up the enthalpy of combustion for 1 mole and multiply it by 2 or 3 or 4. Comes in handy. I see in the notes I left a place for calculating the enthalpy of a phase change, so let's just do one problem or two for grins. So let's say we have, I'll make this a little bit smaller. Let's say we have 4 moles of water. That's a liquid, and it's going to become a gas. How much energy would we need? So when water becomes a liquid, this is the equation, and it would have a certain enthalpy of, when water becomes a gas, of vaporization. So we can't figure out how much energy we need until we know the molar energy, the energy for 1 mole. We have to look that up. We need, or else we'd have to go in the lab and do a bunch of experiments, and that would be tedious. Someone's already done this. So let's pull up the value of the molar heat of vaporization of water going from a liquid to a gas. We'll pull that up. I grabbed this table from Wikipedia, but in class tomorrow we'll look at the tables in the back of the textbook. And here we have water. They give us the boiling point at normal pressure in Kelvin, Celsius, and Fahrenheit. We don't really need that. Here is the heat of vaporization, 40.66 kilojoules per mole. 40.66 kilojoules are needed to vaporize 1 mole of liquid to 1 mole of gas. We're going to use this number, though I'm going to make this table smaller. So if we have 4 moles of water, that's a liquid, and in order to vaporize 1 mole of water, that's a liquid, it takes 40.66 kilojoules. We would then multiply and find out that to vaporize 4 moles, it would take 162.6 kilojoules. What if we had, instead of 4 moles, what if we had 36 grams of water? So instead of 4 moles, we have 36 grams of H2O, that's a liquid. Well, then we would have to change our 36 grams into moles before we could use this molar ratio, this molar piece of information. This is heat necessary, enthalpy necessary to vaporize 1 mole. It tells us information about a mole, not about grams. So we would change our 36 grams, I'll do it over here. There are 18.02 grams of water in 1 mole. This is going to end up being 2 moles of H2O. And then we would substitute, if we were working with 36 grams, we would use 2 moles, and this number would be different. It would be 2 times 40.6, or about 80. Okay, what if that was for vaporization, but we can also talk about melting or freezing. And when we talk about going the other direction, let's stick with vaporization for a second. If we wanted to know how much energy would be released if we went from a gas to a liquid, the heat of vaporization would tell us how much heat was released. But when we are vaporizing, it's endothermic. When we are releasing, we're going this way, and therefore this becomes exothermic if we're releasing, if we're cooling down. I'm going to copy this slide. Again, I took this, we'll look at our tables in our book. This one happens to be from Wikipedia. Here is the, hope this doesn't, heat of fusion, and here's water, and this is in calories per gram in this side, and joules per gram. So notice this is joules per gram, it's not joules per mole. Your heat of fusion could be given to you per gram instead of per mole. It doesn't matter to you, you can convert back and forth from grams to moles. In this case, we were told the heat of fusion in joules per gram. In the other table, it was kilojoules per mole. So it's important to look at your units. This is telling you how many joules you need to melt just 1 gram of ice. We have 36 grams. So if we need more room. Let's make this smaller. We have 36 grams of solid ice. And in order to melt 1 gram, it requires 330.55 joules. So to melt 36 grams will be 12,007.8 joules, which is 12.0 kilojoules. Okay, this is review. This isn't even what the chapter talks about, or heats of formation. So I'm going to stop this video here, and then we do need to understand how to calculate molar heats and what's happening when something is going through a phase change. But right now I'm going to stop, and then when I come back we're going to talk of heats of formation, which is different from heats of formation when the substance is formed, synthesized, a synthesis reaction.